Hi everyone, thank you so much for joining our webinar. I'm Anya, I handle business development at K-Mine. And before we get started, I want to ask you to follow our LinkedIn page for the latest news, updates, and details about our upcoming webinars. Again, thank you so much for being here today. So our webinar today is dedicated to stope optimization technologies. We will talk about different approaches in stope optimization and demonstrate how we do it in K-Mine. First, let me introduce you to K-Mine. We established our company in 1994 in Ukraine, and since then expanded to Europe, United States, Canada, and our team is made up of a variety of experts, including developers, geologists, mining engineers, many of whom are certified in NI 43-101 and JORC reporting standards. We also cater to a wide range of clients, from small exploration groups to major corporations, ensuring we provide high quality but cost-effective solutions. At K-Mine, we concentrate on developing software tailored to the mining industry, aiding it every phase of mining exploration, from exploration to production, and also comprises 12 adaptable models suitable for both open pit and underground mining. What sets our solution apart is its flexibility. Whether you manage a small-scale operation or large corporation, you can select these models that fit your needs, ranging from a single model to a complete suite. These models address key functions such as geological data management, surveying, development of optimized mining plans for immediate or future projects. And with ability to integrate IoT devices or dispatch systems, our software can also provide real-time monitoring capabilities. But our software was born from real hands-on industry experience and challenges that we encountered in our consultancy roles. And as I mentioned before, our team features qualified persons who produce reports adhering to NI 43, SK 1300, JORC standards, so it's suitable for various project phases, for example, pre-feasibility or feasibility study, mineral resource estimation, preliminary economic assessment, and others. We also possess deep knowledge in numerous hard rock commodities, especially critical minerals. So if you're interested how our services could enhance your project, please leave a comment below or use the contact form on our website to get in touch. So if we take a look at our agenda, we will cover mine optimization from general strategies to enhance efficiency, then integrating geological and economic factors in block formations, and we will talk about K-Mine stope optimization for underground mining and how to handle complex deposit conditions, and integrating these optimizations into comprehensive mining plans. So as we keep mining the easy-to-reach shallow deposits, we're pushing ourselves into the future where deeper deposits are the new norm. This means we having to dig deeper, literally, and use more underground mining techniques. That's really up to the need for smarter underground mine planning and optimization. One key part of this is figuring out the best way to carve out the mining areas or stopes. And this process is called stope boundary optimization, which is crucial because it directly affects how much money we can make from a project. You want to choose the layout that gives you the best profit, all while keeping in mind how you'll actually mine it, the rock stability, and other physical limits. Over the last couple of decades, we've seen a bunch of new algorithms pop up to help with this stope optimization. One of these algorithms is the floating stope algorithm. This algorithm is designed to determine the boundaries of stopes in underground mines, and the core idea is to create a virtual floating stope that moves within the ore body to find the most economical beneficial location. The algorithm first evaluates the economic value of each ore block based on a predetermined cutoff grade. Then it creates two envelopes, the inner one representing the area of the highest ore quality and the outer one encompassing all possible stope positions. The optimal result is selected to be as close as possible to the inner envelope while remaining within the outer boundary. Despite its simplicity, this algorithm has several limitations. For example, it does not account for geomechanical constraints, which can result in overlapping stopes where adjacent blocks share high-grade ore. Additionally, it requires manual adjustments by engineers, and it does not always generate stope geometries that align with real mining conditions. The other algorithm is maximum value neighborhood algorithms, or MVN algorithm. This algorithm was developed to optimize stope boundaries while considering their economic value. It uses a fixed three-dimensional block model and identifies the best neighborhood, which is a group of adjacent blocks that provide the highest economic benefit. The algorithm first calculates the individual economic value of each block, then analyzes them in combination with surrounding blocks. The highest value combination among all possible configurations is selected as the most profitable option. The key advantage of this method is that it prevents the problem of overlapping stopes, which occurs in the, for example, floating stope algorithm. However, its results depend on the starting point of the search, meaning that different initial conditions can lead to different final solutions. Also, this method uses rigid economic block models and does not consider the impact of mining cost based on stope shape or size. Another drawback is the lack of consideration for stope wall stability, which may require additional engineering adjustments. The next approach we're going to be talking about is the sense and topple approach. This stope boundary optimization method consists of three stages: block conversion, optimization, and then visualization. In the first stage, the deposit model is converted into a standardized block model with the uniform element sizes. Then, based on this model, the optimization process analyzes all possible stope configurations. A table is created containing data on potential stopes and their economic parameters, after which the algorithm selects the most profitable stopes while eliminating redundant and overlapping blocks. The method allows for both fixed and variable stope sizes, as well as different selection strategies. Its main advantage is the elimination of overlapping stopes, making it more precise than the floating stope algorithm. However, its effectiveness is limited by user experience. The stopes are selected in descending order of economic value rather than through a global optimization approach. And this can restrict the ability to identify more advantageous combinations of stopes. And finally, we have the Sendayaki and Topol approach. This algorithm aims to create three-dimensional optimized stope layout that maximizes economic value while complying with physical and geomechanical constraints. And this process begins with block model regulation to ensure all elements are of uniform size. The model is then converted into an economic model, followed by a step-by-step analysis of possible block combinations. The algorithm first generates all possible stopes, then assigns them parameters such as ore grade and material density, and next unprofitable stopes are discarded, and the remaining ones are grouped into sets that provide maximum value. The main advantage of this method is that it generates unique non-overlapping stopes while considering both economic and geotechnical parameters. Unlike other algorithms, it allows for variable stope sizes and considers the presence of barrier pillars and levels. However, this method requires significant computational resources, especially for large-scale deposits, which may limit its applicability in mines with vast data sets. So each of these methods I mentioned has its own advantages and own disadvantages. The floating stope algorithm is simple to implement but requires significant manual adjustments. The maximum value neighborhood algorithm, or MVN algorithm, prevents overlapping stopes but is sensitive to initial conditions. The sense and topple approach eliminates the issue of duplicate stopes, but is constrained by its selection strategy. And this Sindayaki topol approach is the most flexible and accurate, but demands substantial computing power. Economic analysis has shown that Sindayaki and topol approach provides the highest profitability. However, it requires just more time to execute calculations. The floating Stope algorithm proves to be the least efficient, as it does not account for many constraints necessitating additional adjustments. The MVN algorithm demonstrated a good balance between accuracy and computational speed, but its main drawback is the lack of flexibility in selecting the optimal set of stopes. The Sense and topol approach achieved a high level of detail, but did not always provide a globally optimal solution. So, as you can deduct from this, the choice of an algorithm depends on the specific conditions of the deposit, the required accuracy of calculations, and the available computational resources. In some cases, the most effective approach may be a combination of multiple methods, allowing both economical and geotechnical constraints to be considered when designing underground mining operations. So let's talk about how we can figure out the best way to set up mining blocks by looking at geological and economical parameters. When it comes to optimizing stopes, it's all about mixing geology and money smarts to keep things efficient and safe. And there are a bunch of ways to decide on the perfect shape, size, layout, juggling things like rock stability, how much ore we can pull out, and whether it's actually worth the cash. One widely used approach is the Matthews stability graph method, which assesses the stability of stope walls based on empirical data from previously mined stopes. This method classifies the rock mass using the stability number defined by three key parameters: rock quality designation, joint set orientation, and stress conditions. Engineers can figure out if a stope is going to hold up by plotting the stability number against something called the hydraulic radius. Basically, it's how the stope's volume stacks up against the exposed surface. And it's a cool trick because it adjusts for how good or bad the rock is and gives a handy guide for sizing things up. However, it is limited by its reliance on historical data and does not directly incorporate economic factors. To address economic concerns, the net present value approach, or NPV approach, is frequently integrated into stope optimization studies. This method checks how profitable different stope setups are. It calculates revenue from the ore we dig out. Then it subtracts the costs of running the show, and cutoff grades are the big deal here. They decide what's ore and what's waste. Studies say using a flexible cutoff grade beats a fixed one, so it boosts how much we use the resources. Plus, it keeps the money side solid. By tweaking stope ages based on the market vibes and ore prices, mines can rake in more profit over time. Another method is the Barton limit span theory, which determines the maximum permissible span of unsupported openings based on rock mass properties. This theory establishes the relationship between the uniaxial compressive strength, or UCS, of the rock and the joint roughness coefficient, or JRC, and the joint alteration coefficient, or JAC. These parameters define the stability of rock bridges within the stope, enabling engineers to design the stopes that minimize the risk of collapse. A key insight from this method is the weaker rock masses require narrow stopes and additional support structures to prevent failure. The Barton approach is often used in conjunction with the Matthews stability graphs to refine stope design criteria. For deposits with highly variable geological conditions, numerical modeling techniques provide a more precise means of stope optimization. One approach involves using finite element or finite difference methods to simulate stress distribution and deformation patterns around the stope. These models take into account anisotropic rock behavior, pore pressure effects, and excavation sequences to predict potential failure zones. By iterating through different stope geometries and analyzing stability indicators such as the factor of safety or FOS and displacement vectors, the engineers can optimize stope layouts to maximize extraction while minimizing geotechnical risk. In addition to structural stability, the economic considerations must include the impact of dilution and ore loss. The equivalent linear overbreak slough or ELOS method quantifies expected overbreak based on the rock mass rating and excavation technique. This approach estimates the thickness of overbreak around the stope boundary, allowing for adjustments in stope dimensions to minimize dilution. Research indicates that using ELOS predictions to refine stope boundary placement, we can reduce unwanted waste extraction by up to 15%, and it would lead to a significant increase in processing efficiency. Backfilling strategies also play a critical role in optimizing stope layouts. Hydraulic backfill and paste backfill methods are commonly used to provide structural support while allowing for adjacent stopes to be mined safely. Studies on backfill mechanics show that the consolidation rate and cohesion properties of backfill material directly affect stope stability. Incorporating backfill parameters into stope design calculations can enable larger stopes to be extracted without increasing the risk of wall failure. A combined approach using geostatistical modeling, stability methods, and economic analysis is recommended for optimizing stope design. By using real-time data and updating geological and economical models, mines can adjust stope boundaries and to improve extraction efficiency. This fits with the modern adaptive mine planning, where stope designs can change based on ore body conditions and operational needs. Overall, optimizing stope structural parameters requires a balance between geological stability and economic performance. And the application of empirical methods such as Matthews stability graph, numerical simulations for stress analysis, and financial modeling techniques such as NPV or ELOS provides a robust framework for stope design. Underground mining operations frequently encounter deposits with irregular geometries, variable ore grades, and challenging geotechnical conditions. And these complexities require a systematic approach to stope optimization, ensuring that ore extraction remains both efficient and economically viable while addressing potential operational risks. So we will explore how modern mining methodologies using structured optimization techniques can actually handle the complexities of variable deposit conditions. Irregular ore body geometry is one of the most common challenges in stope optimization. Is dealing with deposits that do not conform to regular shapes, and many underground ore bodies have intricate structures influenced by folding, faulting, and intrusive formations, making it difficult to define optimal stope boundaries. And traditional manual design approaches struggle with such conditions, often leading to suboptimal or recovery or excessive dilution. To address this, modern stope optimization techniques apply clustering algorithms to group economic ore blocks into feasible stope shapes while maintaining operational constraints. These algorithms ensure that each selected stope aligns with the deposit morphology, avoiding unnecessary dilution from surrounding waste rock. By dynamically adjusting stope dimensions and orientation, the system creates an extraction plan that maximizes ore recovery within the deposit's natural geometry. Additionally, in cases where ore bodies contain multiple high-grade zones separated by low-grade material, we can apply selective mining techniques. Instead of designing large, continuous stopes that include unnecessary waste, software-based optimization identifies the most valuable zones while minimizing dilution. And this targeted approach is especially useful in vein deposits and narrow ore chutes where precision is essential for maintaining economic viability. Complex deposits often feature significant fluctuation in ore grade within short distances, and if these variations are not properly managed, the stope design may lead to excessive blending of high and low grade materials or reducing overall processing efficiency. So to counteract this issue, modern stope optimization incorporates variable cut-off grade analysis, which dynamically adjusts stope boundaries based on ore grade distributions. Instead of using a single fixed cutoff, the system applies economic modeling techniques to determine the most profitable extraction zones. This ensures that high-grade material is prioritized while avoiding unnecessary dilution from marginally economic zones. Another approach for handling variable ore grades is incremental stope design, where stopes are subdivided into smaller sections based on economic ranking. By evaluating each section independently, the optimization process allows for more refined control over extraction properties, ensuring the high-value material is mined efficiently without excessive inclusion of low-grade waste. Faulted and structurally disrupted ore bodies present additional challenge in underground mining. Fault zones often contain weak rock, increased water inflows, or abrupt grade changes, complicating stope layout and access design. In these scenarios, adaptive stope optimization methods are used to create extraction plans that account for fault displacement and discontinuities. These methods analyze ore bodies' continuity and adjust stope boundaries to avoid unstable or economically unviable areas. If a fault cuts through high-grade zones, the optimization system may suggest a modified stope layouts that work around the structure while preserving as much valuable ore as possible. Additionally, mining engineers use block ranking methods to identify sections of the deposit that both geologically and economically viable. Blocks affected by faulting or excessive dilution risks can automatically be flagged and excluded from the final stope layout, ensuring that extraction remains focused on the most profitable zones. To address these challenges, modern mining software solutions streamline the process of stope optimization, transforming raw geological and economical data into practical mining plans. Using K-Mine stope optimization as an example, we will demonstrate how sophisticated algorithms and structured workflows simplify stope boundary optimization, ensuring the most profitable and technically feasible outcomes. So how do we begin? Nothing new. We begin with data preparation and input parameters. The optimization process begins with input data preparation. A block model is used as the foundation, containing information about ore grades, economic values, and mining constraints. Each block in the model represents a portion of the ore body with defined geological properties. The economic evaluation of these blocks is crucial as it determines whether they should be included in a stope design or left as waste. At this stage, the mining engineer sets key optimization parameters, including minimum and maximum stope sizes, mining cutoff values, and ore selectivity criteria. Unlike manual design methods, which require extensive trial and error adjustments, K-Mine automatically processes these inputs, allowing engineers to define multiple scenarios for evaluation. The next step is one of the key steps. It's economic evaluation and block filtering. So once the block model is prepared, the software identifies which blocks meet the economic criteria for extraction. Each block is assigned a net economic value calculated by subtracting expected mining and processing costs from the revenue generated by its contained metals. This approach ensures that only profitable blocks are considered for inclusion in the final stope layout. To refine the selection, the software applies variable cutoff grades rather than a fixed threshold. This allows the system to adjust stope boundary dynamically, optimizing the balance between ore recovery and economic performance. In deposits with fluctuating ore grades, this feature prevents unnecessary dilution while ensuring that high-value material is fully utilized. Okay, so what about stope formation and boundary optimization? With economically viable blocks identified, the next step is constructing optimal stope boundaries. K-Mine uses clustering algorithms to group adjacent blocks into coherent stopes while maintaining predefined size and shape constraints. The system ensures that each stope meets minimum thickness requirements and adheres to the selected mining methods. At this stage, one of the key challenges is minimizing ore dilution. Stope designs that extend too far into low-grade areas can lead to excessive waste extraction, increasing processing costs, and reducing overall profitability. So, to address this, the software incorporates equivalent linear overbreak slough or ELIS analysis, estimating how much surrounding material is likely to mix with ore during extraction. Based on this analysis, stope boundaries are adjusted to minimize dilution while preserving ore recovery. Additionally, K-Mine eliminates overlapping and redundant stopes, ensuring that the final design consists of clearly defined, non-overlapping mining zones. This step is crucial in maximizing efficiency, and poorly designed stope layouts can lead to production bottlenecks and increased operational costs. Then we move into scenario optimization and comparison and optimization selection. Mining engineers rarely work with a single stope design scenario. Instead, multiple iterations are evaluated to identify the most effective configuration. K-Mine allows users to generate and compare different optimization strategies, such as prioritizing maximum ore recovery versus maximizing profitability. The software automatically ranks each scenario based on economic indicators such as total extracted tonnage, net present value, and overall profitability. This ranking enables decision makers to select the best option without manually recalculating financial models for each iteration. Furthermore, K-Mine provides a visual representation of the optimal stopes, allowing engineers to inspect the layout in 3D and verify that it aligns with operational constraints. This visualization helps ensure that mining plans remain practical and feasible when transitioning from design to execution. Once the best stope configuration is identified, the results are compiled into a final report, and K-Mine generates detailed extraction scheduling, specifying the order in which stopes should be mined to maximize efficiency. And the software also produces economic reports summarizing projected revenue, costs, and key performance metrics. Additionally, integration with other mining planning models ensures that the optimized stope layout can be seamlessly incorporated into broader production schedules and long-term mine plans. The final output provides a structured and data-driven approach to underground mining, replacing manual estimation with precise and repeatable optimization techniques. So, stope optimization is not an isolated process. It serves as a critical input for broader mine planning activities, ensuring that optimized stopes align with the production schedules, infrastructure development, and economic targets. Once stope boundaries are determined, they must be effectively integrated into the overall mining plan, considering sequencing, scheduling, material handling, and operational constraints. A well-integrated stope optimization strategy ensures that ore extraction is both technically feasible and economically efficient, preventing bottlenecks in production and minimizing operational risks. So, the integration of optimized stope boundaries begins with ensuring their compatibility with both strategic, long-term, and operational short-term mine plans. Long-term planning defines the overall extraction strategy for the deposit, outlining the sequence in which different ore zones will be mined over the life of the operation. For example, in a high-tonnage bulk mining operation, long-term planning may prioritize deeper, high-grade stopes later in the mine's life, when higher extraction costs are offset by increased revenue from richer ore zones. In contrast, a mine with a significant ore grade variability may schedule a higher grade stopes early in the project to improve early cash flow. In short-term planning, stopes are scheduled for mining based on equipment availability, workforce capacity, and logical constraints. And if a stope is scheduled for early extraction but lacks an established access drift, delays in development can halt production. In such cases, integrating optimized stopes into the mine plans ensures that extraction sequence align with access development schedules, preventing unnecessary downtime. Once the optimized stopes are integrated into the mine plan, the next step is determining the extraction sequence. Proper sequencing ensures that the highest value stopes are mined at the right time while maintaining geotechnical stability and minimizing disruptions. The sequence choice depends on several factors, including ore grade distribution, where high-grade stopes are targeted first to boost early cash flow. For example, if two stopes contain similar tonnage, but one has significantly higher metal content, prioritizing that stope ensures higher revenue per unit mine. Another factor is access development. It involves making sure new stopes can be reached using current infrastructure and planned expansions. For example, if two neighboring stopes are scheduled for extraction but only one has completed access drift, the second stope must be delayed until development work is completed. And the final factor is rock mass stability, which focuses on keeping excavation sequence control to lower the risk of collapses. In cases where stopes are adjacent to each other, removing support pillars too early can lead to ground movement affecting both safety and ore recovery. Production scheduling is then developed, detailing the timing of stope extraction in weekly, monthly, and annual intervals, and this ensures that the ore supply meets processing plan requirements while maintaining steady production rates. For example, a mill designed for 1.5 million tons per year must receive ore at consistent feed rate. If stope sequences does not match processing capacity, production delays and stockpile imbalances may occur. So, optimized stope layouts must also be evaluated for the impact on material handling efficiency. The location and orientation of stopes affect ore flow within the mine, influencing haulage distances, travel time, and transportation costs. If an optimized stope layout does not account for existing ore transport system, additional trucking and conveyor modification may be required, increasing operational costs. In deeper mines, material handling constraints become even more critical. If a stope located far from the main haulage level, additional ore passes or truck ramps may be necessary, adding time and expense to extraction process. In contrast, of course, if the stope are strategically located near haulage infrastructure, ore transport efficiency improves, reducing energy consumption and increasing haulage capacity. In operations that use backfill, stope optimization results might be integrated with backfilling strategies to ensure a continuous mining cycle. The placement of backfill must be carefully timed to allow adjacent stopes to be mined without compromising stability. For instance, in cut and fill mining, stopes are often extracted in a staggered sequence with the backfill placed immediately after ore removal. If backfill curing times are not considered, adjacent stope extraction may be delayed, slowing down production. On the other hand, in bulk mining methods such as sub-level stoping, backfill is used to provide regional stability, allowing multiple stopes to be mined simultaneously without causing excessive ground movement. Different types of backfill, such as paste fill, hydraulic fill, or cemented rock fill, require varying curing times and placement techniques. And if a high-strength cemented backfill is used, adjacent stopes can be extracted sooner, improving mining efficiency. However, if unconsolidated hydraulic fill is used, longer waiting periods may be required before adjacent mining can be proceed safely. Although Stope Optimization focuses on maximizing ore recovery and profitability, it must also align with geotechnical safety standards. Stope layouts must be reviewed in the context of pillar placement, ground support requirements, and overall mining stability. If an optimized stope design suggests extracting a large unsupported void, you should implement ground control method to prevent collapses. For example, in weak rock conditions, larger stope spans may require additional ground support, such as cable bolting or shortgrit application. If these geotechnical constraints are not factored in the stope optimization process, extraction could become unsafe and require expensive remediation efforts. Conversely, in highly competent rock masses, wider stopes may be feasible without additional support, reducing cost and improving efficiency. So once we've got those optimized stope layouts locked in, they get rolled into the detailed operational plans that guide our day-to-day mining work. And here how it looks like. We put together drilling and blasting plans for each stope, making sure the fragmentation is just right for smooth material handling. Then we map out the access development schedules to keep everything flowing logically, tying into the haulage and ventilation setup so nothing can get bottlenecked. We also sync up with the ventilation and dewatering teams to ensure an underground water air quality and water systems are on point for safe extraction. And finally, we align it all with ore processing needs, keeping the ore delivery steady and consistent to hit those mill throughput goals. So this structured approach ensures that stope optimization results are not only theoretical models, but practical, executable plans that contribute to overall mine performance. So I think that's it for today. Thank you guys for joining in. I'll see you next time.